לקחנו את פתרון שוורצ'יט. מטריקת שוורצ'יט. ds squared is a minus 1 minus 2 gm over r. C squared. cdt squared plus 1 minus 2 gm over r. C squared. Minus 1 dr squared plus r squared d omega squared. So we said we have two interesting, let's do a recap on what we did. We said there are two interesting radii here. One is r equal to 0 and one is r equal to gm over c squared. That's called the Schwarzschild radius. That's called the singularity. We will thoroughly discuss both of them. Not today. And then we start to look at motion of particles. Particles in Schwarzschild metric. And we said, well, we started by putting down the geodesic equation. There are 4 of these. But we say that it's not going to get us too far. Instead, we looked at the conserved quantities, which are given by the Killing vectors. And we said that there are 4 Killing vectors. Right? 4 Killing vectors. One which is associated with the energy. K mu 1 0 0 0. So K mu dx mu over the lambda is 1 minus 2 gm over r dt over the lambda, which is a constant of motion. I call it E, the energy. So it is associated with the time symmetry. The 3 Killing vectors are associated with conservation of angular momentum, essentially with rotational symmetry. So 3, 2 would correspond to the direction, which essentially means that the motion of particles, test particles, right, in Schwarzschild metrics would be in line with the plane. So theta direction 2 means motion is in the plane. And we select theta to be pi over 2. Then 1 is associated with the magnitude. That was a K mu 0 0 0 1. L is the mu, so we just have essentially that gives us the r squared d phi over the lambda, so equal to another constant which we call L. Of course, we know physically that E corresponds to the energy, L corresponds to the angular momentum, but from a mathematical perspective, these are constants of motion. Yeah. Okay. Then, in order to analyze the trajectories week, we used the metric compatibility, which is essentially stating that epsilon minus g mu nu dx mu over the lambda dx mu over the lambda. Epsilon is equal to 1 for massive and 0 for much less.
How does the difference appear?
What?
How does the difference appear? How do we get the epsilon from the...
Maybe the simplest way to think of it is in special relativity of the eta, right? So you have u mu. We derive that, right? If you replace lambda with a tau, right? You have what's written here is u mu is equal to epsilon minus epsilon, right? And we derive that in special relativity. When you add particles, you have this is a 1. When you have photons, this is a 0. And since this is a tensorial equation, which is correct in one frame, it will be correct in any frame. Right? So go back to what we learned about in special relativity, and you'll find it there. 4 vectors of, again, if you even go to the I don't need to go to any frame. Just is anybody who's not happy with that? These are things that I thought we should be quite familiar with. So now I just plug in the metric into this equation. Using this constraints that we have there. And we got that the minus 1 minus 2 gm over r. That's g00. Then we have the t over the lambda. I omit the c, of course, right? It's 1 squared plus 1 minus 2 gm over r minus 1 dr over the lambda squared plus r squared d phi over d lambda squared is equal to minus epsilon. Then I multiply this equation by 1 minus 2 gm over r, and use the definitions that we have here. Write down minus e squared plus dr over the lambda squared. Right? I multiply by 1 minus 2 gm over r, have minus 1 minus 2 gm over r squared, dt over the lambda squared. This is e squared. This is gone. Plus 1 minus 2 gm over r. Then r squared d phi over the lambda squared. You just write it as L squared over R squared, and then have the minus epsilon term, that's just moving it to the left. So epsilon is equal to 0. And I like this equation because I can write it as multiplied by 1/2. So I write it and I move e to the other side, so I have 1/2 dr over the lambda squared plus v of r is equal e squared over 2. And v of r is what is written here, which I'm going to expand, multiplied by 1/2. So it's a 1/2 epsilon minus epsilon g m over r plus L squared over 2 r squared minus gm L squared over r cubed. So what did I really do here? I am looking for trajectories. How do particles move in the Schwarzschild metric? And I wrote down an equation, which is a conserved equation, which essentially I gave it a form for one-dimensional. Of course, the motion is not one-dimensional. The motion is three-dimensional in space, but it's limited to a plane, so it's really two-dimensional on that plane with some effective potential. And the potential is exact. It's written like a power in 1 over r, but there are no additional terms. These are all the terms that there are. And again, epsilon is equal to 1 if you're talking about massive particle. This equation is general enough to include epsilon equal to 0 would be massless particles, namely photons. Without this term, what we have here is Newtonian. Right? This is in fact identical to the Keplerian potential up to the half here. We don't care about this. But the potential is constant. But the potential itself is identical to the Keplerian potential. We have this extra term, which is really the whole difference between general relativity and Newtonian mechanics. When it goes to massive particles. Yes?
For massive particles, Newtonically, the angular momentum is 0, right?
Yeah, well,
But for massive particles here,
yeah.
the angular momentum.
We'll get to that. One step at a time, we'll get to that. By the end of this lecture, this will be finished. I hope. Okay? I just want to make sure that you're all with me and we don't get confused, because this is something that can be confused, especially if you didn't get it properly in the first. Right? We're going to analyze this in 1D. Right? 1D means it's a function of r. Right? Everything, the potential is a function of r. But the true motion is not 1D. The true motion is in a plane, which is 2D. Right? So let's say we have a source of potential here, star. The motion will be something like that. If it's a closed orbit, right? Or it could be something like that.
Is it 3-dimensional because we have time?
It is, but it's limited, we said, because of the conservation of angular momentum.
I'm saying that time is also
No, when it comes to the motion of particles, we're looking at the trajectories of the particles, so we don't look at them at the time right now. It's there, of course. We'll get to that also. But right now, we're just looking at the trajectories. We're analyzing what type of trajectories we can have in Schwarzschild metric, right? Now, the true trajectory looks something like that, right? This is r. It's a function of lambda, right? We're going trajectory. We have a parameter lambda, and this is r, which is a function of lambda, right? Or there. We have this orbit, those bound orbits. This is r as a function of lambda. We're doing what we used to do. We take an orbit, we just parameterize it with some parameter lambda. Okay? Now we're just looking at, don't get confused, this can be a bit confusing. We're just looking at r as a function of lambda. With that potential. Okay? So if this is the potential, let me draw that potential. I'm going to make 2 draws. You know what? Let's focus on 1 draw. So we start by massive particles. Epsilon is 1. So this is V of r, it's a function of r. The units are, of course, gm over c squared. It's the natural units that we have here. And the first, I'm going to draw just a Newtonian potential. So just without that term. Just a Newtonian potential. Newtonian potential, just the first three terms. What does it approach us when we go to infinity? Half, thank you. Epsilon is 1, it's a massive particle. Right, so it's a half. Right. What does it approach for 0? Or goes to 0?
Minus infinity.
What? We're just talking about Newtonian potential. Right? And then the rest, right? And you see that there is a minimum. Right? That's the thing that you're used to, right? It's the same. Let's say this would be L equal to 1, it will be exactly 0. If L is equal to 1, you get here exactly 0. You're familiar with that, you saw that in first year. What?
Would it equal 0?
Yeah, you just put L equal to 1. Right. If you put L equal to 2, it will have the same behavior basically. So 2 will be.
What about?
It's a function of L, depending on L. So L equal to 3. And L equal to 4. Actually, no, I did not put it properly. L equal to 3 will already be about this. No minimum L equal to 3. See L equal to 3. Then you have L equal to 4. What about the full geometry? Let's do it right. What does it approach at infinity? When R goes to infinity? Half, right? It's the same, right? When R is very large, it will approach the same thing. What does it approach when R goes to 0? Minus infinity. So now there is a big difference. But the big difference, of course, is pronounced only at small r's. In fact, you can easily see that when R is equal to 2 in units of gm over c squared, then v of r goes to 0. So yeah, now it's a function of L. If L is equal to 1, you get something that looks like that. This approaches infinity. If L equal to 2, it will look somewhat higher.
Maybe
Hold on.
next room.
Hold on. That depends on the value of L. If L is equal to 3, you still have something like that. If L is equal to 4, then yeah, actually I'm not drawing it very nicely. If L is equal to 4, you should get something that looks like that. There will be a small minimum, a small maximum here. L is equal to 5, another maximum. Yeah, the idea. Draw it nicer and So this is sketch.
How do we get again that's for RDL?
What?
How do we get again for that for RDL? R equals to.
I just plug in the file here. Just a plot of this this problem.
Yes, but it doesn't seem that it's R equals 2 for every L. We get the same value.
So it does. Check it out. Check it out. It will cancel out. Check it out. It's quite easy.
Using what? Using only this expression.
We put R equal 2gm.
2gm over c squared.
Over c squared. C is 1, so just 2gm.
Oh, okay.
So half epsilon minus half epsilon, L squared over
Okay.
2gm, and this 2 will just cancel. So you always get the 0. Okay, this one will cancel with that. This one will cancel with that. You'll always get the 0. What about particle motion? Let's start with the Newtonian one.
Oh, yeah, it's not going to be in closed loops.
Why don't R less than 2?
Wait. What types of motion you're familiar with Newtonian potential?
There is a bound motion in ellipse.
There's a bound motion,
and then
and
there
that depends on what?
on
On the energy, which is really the orbital energy. Don't forget that. Right? It's the energy versus the potential. Right? So if a particle is here, what type of trajectory we have? It's a circle, right? So this is the source of the sun. Right? This represents a spherical orbit. If the particle's energy is higher,
an ellipse.
that, right, there are 2 radii, minimum and a maximum. So R min and R max. So if I draw them, this will be R max, this will be an R min. And the trajectory of the particle will be in between those, right? So we'll have something that looks like that. Not a great door, but I hope you get the idea. Right. We have bounded orbit between the minimum radius and the maximum radius, which radius that depends on the angular momentum and depends on the energy of the particle. Right. So this is what these quotes really mean. What if it's if the energy is higher enough, higher than half?
It's going to be an hyperbola, go to.
What?
Just on a scale.
Right, so the particle will move in, reach a turning point, and go back. What's the true trajectory look like?
Hyperbola.
Right, it will come from infinity. Will be bent by the gravitational potential and then go to infinity. Right. Now you may have seen that. What type of trajectories are allowed in Newtonian mechanics?
Conic section.
Conic sections. Everybody's familiar with that. Conic sections. So you have to go 2 cones. Right. If you cut it like that, you get the circle. Cut it like that, you get an ellipse. If you go along that, what do you get?
Straight line.
Yes. If you go like that, what do you get?
Hyperbola.
Parabola.
Up.
Parabola. And if you go like that, you get. Sorry, like that. What do you get? Hyperbola. Yeah, everybody's familiar with that. It's just a fun game. Okay, so this is the type of trajectories we have in Newtonian physics.
Where is free fall?
But if you don't have enough energy, just fall into the minimum of the potential.
See?
Fall to the minimum of the potential. The idea is that you have enough energy. Free fall basically means L is equal to 0. If you have some angular momentum, then you'll end up with somewhere between the minimum and maximum. Gradient, always. Okay. You're right, if L is equal to 0, essentially then you get minus 0. Just this way. If L is not 0, you never get it. Okay. What happened here? So basically, this is set by V of R is equal 1/2 this. Same. So exactly. Sorry, this is the turning point. Inside here, so the turning points.
So which one are you analyzing, the GR or the Newtonian?
No, now there was still the Newtonian one. Just finishing the discussion about the Newtonian. Newtonian is something which you're supposed to be familiar with from first year studies. That's just a reminder. Anybody who's not familiar with that? Seem happy enough. Okay. What are the conditions for a circular orbit? And still stay here for a second. So circular orbit. When are we going to get a circular orbit? The minimum, the potential, or the maximum. So what do we do? Take the derivative of V of R and we compare it to 0. So circular orbit is, let me erase this part here. Circular orbit is you get when dV over the R is equal to 0. That means that RC is equal to constant. dV of the R equal to 0, just take that, take the derivative, and I'm going to multiply by R to the 4, and we end up with epsilon GM R circular squared minus L R squared R circular plus 3 GM L squared gamma is equal to 0, where gamma is 0 for Newtonian and equal to 1 for GR. Just took the derivative here, then I multiplied it out with 4 equal to 0. How do we know if a circular orbit is stable? It's a minimum of the potential, which is another way to say the second derivative needs to be negative. How do we know it's unstable? Well, it's a maximum. What does it mean, stable or unstable? Just to make sure that it will stay there. It will move in a circular orbit, but a small perturbation will either be disappearing or take it away from this orbit. So that's the meaning of stable. Circular orbit, Newtonian potential. So this is 0, so Newtonian potential, circular orbit is when RC is L squared over G. always stable. Now,
Is it C squared or L squared?
sorry, what?
Is it C squared or L squared?
Where were you?
In RC. It's L,
RC
right?
is L squared over GM. And just plug it in, right? Gamma is equal to 0 in Newtonian. Now in GR. GR, we actually have to solve it because gamma is equal to 1. So we have a quadratic equation, so you know how to solve quadratic equations. R units of C squared. So if V over dr equal to 0 means that RC now is a function of L. So L squared plus minus square root L to the 4 minus 12 G squared M squared M squared. Divided by 2G.
Set epsilon.
Yes, epsilon to 1 because we're talking about massive particles. Epsilon is 1, and then GR gamma is also 1. This is just for shortening. Writing two equations, one for GR, one for Newtonian. Now we can take the limit where L goes to infinity. L is the orbital angular momentum. So first of all, there are two solutions. Right? For large enough L, right? If L is too small, we won't have them. Right? For large enough L, there are two solutions. It's not really plotted properly here. Or it's, so I have two solutions. One of them is going to be what? It's not Newtonian, but it's going to be very close to Newtonian, right? We have two solutions. So two solutions.
One is stable and one
Right.
is
This one is going to be a stable solution because it's a minimum of the potential. This one is going to be unstable. It's a maximum solution, the maximum of the potential. So in the limit where L goes to infinity, you can Taylor expand that and write it as RC is L squared plus minus L squared 1 minus 6 G squared M squared over L squared divided by 2 GM. So it's an L squared over GM and 3 GM. So when L goes to infinity, we'll have one circular orbit which will be at very large L, and one which will asymptote into 3 GM. Right, you see that? So when L is very large, potential will look something like that. here. VGM, and one solution somewhere here. Goes to infinity. This is a Taylor expansion. L squared and then square root and just expand it by Taylor expansion. Yeah.
Would we guess that it would be at 3G and not 4G?
You don't need to guess. The equation is quite simple.
Oh.
Just solve the equation and that's what you get. It's not something that you need to guess.
No, but it could be anything. There's no reason.
Not
The
understand what
calculation gives you
could
three
be anything.
inputs.
It is.
If you're just trying to understand the system without solving the equation, there is no reason that it would be 3 and not any other constant.
I don't know what about reason or unreason. I'm just saying that this is the equation, and you just solve the equation. You just solve the equation. It's a very simple equation to solve, right? We did worse than that in this course, and I'm sure in other courses as well. And that's the solution will be fine. Yeah.
First solution shouldn't have another element.
What?
First solution shouldn't have another element.
No, why?
You
Yeah,
can't
but
choose
plus.
enough.
Yeah, it's a correction, but when L goes to
Positive
infinity, it's
Newtonian,
when L goes to infinity, that is the same as the, of course, the Newtonian solution.
Okay, and you said that there should be another element.
Yeah, there is, but it's small. Of course there is. You can see it from here, right? But it's a small correction when L goes to infinity. So this is, as you can clearly see, and you're right, this is the same circular solution that we have for the Newtonian case, but we have another solution, 3GM. Right. Remember, this is not really relevant to our solar system. Why? Right? Because at 3GM, the Schwarzschild metric is not valid because this is inside the sun. But it's a generally true solution when the source of the potential is within this 2GM over c squared. Okay? Now what happens? So this is the solution for RC. Now we get, this is the exact solution. When L decreases, now this was for large L. L goes to infinity, then we find two solutions. This has a name, by the way. No, what we call that? It's a photon sphere. Might have heard that. We'll get that. We'll get there in a second. Now let's look at L goes down. Now L decreases. So when L reaches what? You can see from here. So when the two solutions merge, square root of 12, right? So when L is equal to square root of 12 GM, right? The two circular orbits merge. Right, because the discriminant here is 0. And then what is RC? This is 0, so just L squared over 2GM. It's equal to what? It's equal to 6 GM. This has a name. You know what we call that? That's called ISCO. Innermost stable circular orbit. Why is it important? Now, we need to go back and think as physicists. What happens in reality? When we look at black holes, we take pictures of black holes. And what do we see? I'm now erasing that. I need the board.
Something, and then nothing.
What happens around the black hole? So we have a black hole, right? And what do we have around it? We have accretion disk, right? We have gas that is spiraling in. Right? So we have some gas there that spirals in. And what happens when the gas spirals in? There is viscosity. Right? It heats up. Right? So it heats up. And then what happens when it heats up? It radiates. First it emits radiation, and then another thing that happens because of the friction. What happens with the friction? It is lower. It's losing angular momentum, right? Because of friction. We have a gas here. There is a friction here. So some gas, external will go out because angular momentum is conserved. So some gas will get out of here, right, away. But the gas that loses the angular momentum by friction will spiral in, right? And because it gets hotter, then it emits radiation. Right? Thermal radiation. And we see that. That is the radiation that we see. This is what telescopes see. Telescopes do not see gas, they see photons. Right? So they see radiation. And when is the hottest? Of course, when you get further in, you're seeing stronger and stronger radiation, higher and higher wavelengths, typically in the X-rays, until the ISCO. Right? Because once you get to the ISCO, what happens next if you continue to lose friction, to lose angular momentum? You fall in. So that means that most of the radiation will come where? From the ISCO. So this is something which we actually measure. Right? Now, our ISCO depends on what? Only on the mass, right, of the central object. So we have a way of estimating the mass from what we're seeing. Cool, isn't it? It's even cooler than that. We won't have time to discuss it because that's not part of the syllabus of this course. But of course, there is an ISCO if the black hole is rotating, right? And it's different value. It's actually smaller. So in the last, I don't know, decade, maybe less, 5 to 10 years, the technology has matured such that you can measure or estimate even the spin of the black hole by estimating what is the ISCO where the emission comes from. But you need to have, if you have other measurements of the mass, which often you do have. So this is one technique which is used by astronomers today. Well, it's not something which is too new, to estimate the mass of black hole by looking at emission, which we know comes from the ISCO. So this is actually quite meaningful, this number. And often if you go to astronomy talks, if you do, sometimes people just use that without really explaining what it is. So this is what it is. Yeah?
Even though the closer the gas gets to the black hole, it's getting hotter. Also, the gravitational redshift gets stronger. So
yeah.
Why does one
get hotter faster? Gravitational redshift. Okay, so that's the ISCO. So this is the smallest possible radius of stable. This is the smallest possible radius of stable orbits. Let's measure. What is that? Before we do that, so let's again do the same game we played about the trajectories. trajectories in GR. So we said, as far as circular orbits, we said we have two, right? One here, and one here. Right? So the trajectory, if we have some object, say another object is a black hole. What does this trajectory look like? It's a circular orbit. It's just a circular orbit. Put the point here that really represents a circular point. What does this trajectory look like? Also a circular orbit, right? But this is unstable. Now, this is called, I mentioned it already, this is called the photon sphere. Okay. Why is that? Yeah, photons can. What really happens here? I don't know if you can see that right away. Yeah, that's true, but the other way will be to look the same. I'm jumping a little bit. How? Okay, what I mean is now intuitively, how do you understand that? Intuitively. I don't know if you see this picture you have. How can you have an orbit which is circular yet unstable? Stable, you're sort of used to, right? You have this potential minima. Earth is rotating around the sun. All the planets are rotating around the sun in potential minima.
So zero to exactly its position.
What?
Something causes you to be exactly.
Okay, so I guess you've seen this picture. You've seen this picture of black holes before. I just want to get to make sure that it's in your mind. So you've seen this picture of black holes before, right? You have this black hole, and then the space looks something like that, right? Right? You've seen that before, you know. Right? That's the metric we're talking about. Now what happens if you go to 3RG, you're somewhere here, you're orbiting like that. So the space-time is curved in exactly the right way that you'll be moving. Remember, everything is along geodesics, right? So don't get confused. You can still move on to lower orbits and then get out if you're accelerating, as long as you're not crossing this 2GM. Right? Exactly. You're sort of moving on a region where everything happens to curve in such a way that you'll continue to move in this trajectory forever unless you're perturbed. When you're perturbed, right, you either go spiral inward or get out. Okay, this is the picture you should have in mind. What really happens. This is the mathematical description, but this is maybe a more intuitive way of seeing it. Yeah. Okay. So this is sort of looking from the up. This is this. Okay. If you're looking about bound orbits, right? So same. We have our mean and our max. Same as we had before. Our mean, here's our max. And the true trajectory of the particle look very similar to what we had in Newtonian. Bounded between R min and R max. Okay. Just make sure that you're with me, because I'm going to having these plots here which are sort of capturing physics but in a certain way, and this just tells you what really happens there. But this and this are the same, just make sure that you see that. Now we also have unbound orbits. about this orbit, for example?
Scattering.
It's an unbound orbit, right?
Scattering.
It will be a scattering, but now it will be it will not be a part of a conic cut, right? But you may have something that looks like that. Makes sense here. Right? So it's slightly more complicated to describe because on your end you have this orbit as well. One of these orbits. So this will be something that that just goes and spirals. Just goes like that. Do something. Again, this is the energy versus the potential. Now the energy, we're talking about orbital energy. Right? Energy associated with the orbit of the particle. The same would go for photons, right? It's not the photon energy, but energy associated with the orbital motion of the photon. And the potential is the potential. Right? That's where we are. Yeah. Okay.
So
Yeah.
it's kind of unintuitive that if you increase the energy, then it gets extended.
It's the energy versus the potential. So you need to cross it. Again, it's the orbital energy. So it's a way. It's basically where you're aiming yourself relative to the potential. If you're starting from here and you're going in this direction, you'll fall in. If you're starting from here and you're going in that direction, then you might be spiraling in and go out. So you have to think a little bit about
Because the direction changes L.
what?
The direction changes L.
Also L. So
Okay.
it's E versus L. E. Okay, so it's well, I guess what I want you to think a little bit about that because it's now the mass is trivial relative to everything else we did in this course. The physical meaning is important, so it's important that you see the true physics around here, what it really means, all these things. Okay. What about massless particles? So, any more questions about that? These are all massive particles, so you can go.
Is it linear equation?
What?
It's a linear equation.
Yeah, nearly right. For massless particles, it's going to be much simpler in a way. So now I'm going to look at it's quite straightforward. If you do the same trick for the Newtonian, right, and just put here epsilon equal to 0, you really only have that term in Newtonian physics. So for Newtonian,
In Newtonian physics, massive particles don't have angular momentum.
yes, hold on. In Newtonian physics, if I look at the potential, right, I have that. Right? This is the potential. This is correct.
No potential.
Yes.
They don't
This will be
have
the
angular
potential. I'll have L squared over 2R squared, which will look
But
pretty straightforward. Hold on. Right. Yeah, they will 1, L equal 2, L equal 3. Okay. Right. What would be photons' trajectories?
Straight line.
Straight lines, right? So it will be like that until you reach that
What about the
and go back.
the-
Now here's the thing you're missing, right?
It's up to the fourth.
Well, what?
About the fourth.
This is GR. Talking about Newtonian potential. Right? Newtonian potential is just D3. Here's what you're missing. That's why it was important for me to draw these plots. It goes here and goes back here. What do the photon trajectory? What is the photon trajectory really looks like in Newtonian potential? You know that, right? Straight line. So why do I plot it like that? And what is the meaning of L here? Remember, this is R. Right? What is R? This is R. Right? So again, I am quantifying or specifying the trajectory by some parameter along the trajectory, lambda. Right? So what happens to the photon? This is really R of lambda. Right? So photon is here, R is large. The photon gets closer, closer, closer. You have an R mean. Again, for some lambda. And then R goes and increases again. Right? So this plot represents exactly that motion.
You also have straight line which are emissions.
Right.
Emissions. You also have trajectories which are straight line which are straight towards the sun and straight away from the sun because we know the sun.
And I will
is
put
far
L
away.
equal to 0. So L really represents how far I am, how far the trajectory is from the center. When L is equal to 0, then indeed I will get all the way, essentially.
What
Again.
is the potential? You drop the GM?
Again, epsilon is equal to 0. So this is 0, this is 0, and this is the GR term, remember? We said that. This is a completely Newtonian potential. That's what you get when you look at Keplerian orbits. This is the only contribution of the GR. Everything we work very hard to find the Schwarzschild solution. The only contribution will be here, these two. But this only contribution means a lot. Okay. So this is massless particle in a Newtonian potential. That's the trajectory. That's how we're going to describe it. Yeah.
Are there ideas to add more terms to this potential? Like more than
No, I said that. This is exact. We get it as an exact solution when we derive it. It's not an approximate.
Yeah,
It's written in terms of like a series in 1 over r, in powers of 1 over r. But it's not. This is exactly. It's a final. There's no more.
in GR, yes, but
GR.
I mean like generally, whether this is thought of like adding steps.
It's beyond Einstein, but that's not. This would not be. Go back. Schwarzschild is a solution. It's the only. We said this is the only solution, vacuum solution, for a spherically symmetric. It's the only spherically symmetric vacuum solution to Einstein's equation. Now you want to solve Einstein's equation, find another solution. Go ahead and find it, and then you can explore what is the consequences of this solution. But for this solution, this is the solution, the exact solution, and what we derive is exact. It's the motion of particles in that metric, in Schwarzschild metric. That's what we're doing now. You want to add more terms? That's not Schwarzschild metric. That's a different metric. Find another metric that solves Einstein's equation, and then explore the consequences. That's fine. The only thing I can say, and we'll say it today, I think we'll have time at least partially, right? Obviously, as I told you more than once, physics is an experimental-based science. Right? This had been tested experimentally. Otherwise, it would not be considered physics, not considered valid physics. Right? We're going to discuss shortly when we finish discussing analyzing trajectories what experimental casts we have. And we do have. Otherwise, I would not spend a semester standing in front of you talking to you about maybe nice mathematical things that will be in the Department of Math. Department of Physics, that's because it has a physical meaning that we can measure. If we could not measure, or if we measured and we found something which is different than that, I would not hide it from you. I would tell you that. We did not. Model things we measured and we know that we don't understand, such as the dark energy, dark matter. This is something which we measure and we understand. Is that clear what happens here? This is the true trajectory. This is the way we describe it in this V diagram. Right. So what this really means, right, is that this is dr over the lambda is smaller than 0, right? It gets closer and closer. And from here, this is the r over the lambda greater than 0. So it's representing this half. Yeah. Okay, what happens in GR? So in GR, this is the Newtonian. And what about GR? GR, we have these two terms. So again, when we go to infinity, right, what do we have? Yes, but it's the same approach. We have the same thing as without the GR, right? This term wins over that, right? And when we go to 0, right, now it gets minus infinity. And at what radius does it become equal? Exactly 2g. Exactly 2g. Right? So r is 2gm over c squared. Right? Regardless of the value of L, right? It's independent of L. It all goes to 0. So for different L's, the potential would look something like that. One and 2 and right. So unless L is equal to 0, which is basically going straight in, then there is always a barrier. But photons that are energetic enough, energetic again in terms relative to the angular momentum, so you have to be careful in how you interpret that energetic, right? We'll always be able to cross it. So we have that type of trajectories, we have that type of trajectories, and we have same that we had before. Again, when L goes to infinity, so when L goes to infinity, this goes to 3gm. So the type of trajectories we have. And for this one, we already showed that, right? We have the center, and this will be a circular orbit around the center, 3gm. For this one, now come the key difference. what is the motion of the particles, of the photons now? They are not in straight lines. I mean, they are in straight lines, but they're just in straight lines, but curved space. Right? So the orbit, for example, this orbit, right, would look something like that. And that orbit here, right, would look something like that. I forgot to break. I think on Thursday. Okay. It's okay. So again, this orbit here essentially means that photons can orbit there for you. Right? Now, you don't expect to see that's why it's called a photon sphere. Now, you don't really expect to see it. Why not? Because it's unstable. So even if there is some source of photons there, any small perturbation, any gas that will pass through will take them away from it. So this is more of nice mathematics. You can see like nice simulations that they show that. But in reality, you don't expect astronomers to look and see it. But it's there. Physically, it's possible. Yeah.
Even if there was a photon sphere, we still wouldn't be able to see it. Because the photons are there, though, anyway.
Well, it's a yes and no. Yes, because unless you're there, so you won't see it. No, because if you have like a small perturbation that will take away, so the photons could accumulate there, which again, it's not really possible because it's not stable, and there is some perturbation that takes them away, then you might see a bunch of photons. You're right, it's not something which is real.
It could be created faster than it is.
I don't know of any practical way. Maybe even. Yeah.
The R maximum is where the photon sphere is, right?
R maximum? No.
So the R circular,
R circular is right.
which is the maximum of that graph.
No. Yes. If L goes to infinity, this grows with L. So when L goes to infinity, this will be a 3GN. If L is less than infinity, then it will be something. So
All the maximum.
I don't see why the maximum point of VR ends on L.
Yeah, you're right. It will cancel out. Then maybe it's independent of L. It's always the same. Yeah.
About the photon sphere. Imagine you have a light source that's constantly sending photons towards the left.
Yeah.
Like 100% of the time. Now perturbations could take out the photon sphere, but if there is a constant supply of photons, then it should be there.
But they will not stay there because they don't start from there.
But there are always new photons to replace the old ones. So
well, yeah, but the photon, okay, it's not practical really. Unless you want to engineer it somehow in real life, again. Remember one more thing, right? All we talk about now is geodesics, meaning that nobody's interfering. There is no acceleration, there is no engine that operates there, there are no additional things that could modify the picture, like strong magnetic field or something. Right? This is pure geodesics, no additional sources of force are applied. Right? So real life obviously is more complicated, but you get the basics here. One step at a time, as I keep on telling you. All right. More on that? I mean, we're getting more and more things that stimulate the imagination. So just have to think of these things at home and spend more time and whatever. All right. And, make the difference between real science and science fiction. That's what I'm saying. Because some of the things you might have heard is termed in science fiction books or movies or something. Now we're doing the real thing. These are the correct things.
What does science has to say about R equals 0?
No, we're not there yet. We'll discuss that in a few lectures. But really not too much, to be honest, because that's where once you get the density gets above the Planck scale, known laws of physics are not valid anymore. So we don't really know that. Yeah.
How can we, where we can see they have epsilon, the constant?
This is just, you don't really see it just a mathematical way. What the whole purpose of this, everything we did so far, was to use techniques that you're already supposedly familiar with from your first year studies, and show you that we can generalize. You can use the same techniques to study trajectories in GR. Okay, the same thing. So epsilon really is just, this is just what we got from the equation, right? Again, we wrote down, we saw basically this is a solution of, not solution, this is a geodesic trajectories in Schwarzschild metric. That's what you get. So it's really just a constant. At the end of the day, this constant doesn't mean too much. It's just how do you interpret that your energy. Again, energy associated with the orbital motion. I keep on saying that because it's got nothing to do with the photon energy. Photon will have energy depending on their frequency, but this is the energy. This has got nothing to do with that. This is the energy of the associated with the trajectory. So really with the timeline killing factor that we have. Right? Questions, guys?
Assume that the velocities are relativistic, like speculative.
Don't say anything about this. That's a nice thing. Solve that. You know how to do that? To work out for the non-relativistic cases. Right. More? Okay. It's been, I thought we might go faster, but it's perfectly fine. Classical tests of general relativity. So I keep on telling you that again, everything we do here makes sense because it can be tested. It had to be tested. It had to be proven. How can you test GR? What? I cannot hear you. Gravitational lensing, yeah, that's one of them. So that would be reflection of light. What else?
Time dilation, redshift illusion.
What?
Time dilation, redshift illusion.
So yes, first is gravitational redshift. We discussed that. Gravitational redshift of spectral lines. That would be the first one. Second is deflection of light by the sun. The third one, which you sort of said, it's precession. Precession. Precession of the perihelion of the inner stars. What's a perihelion? What is a perihelion?
It's radius which is the closest to the sun.
Very good, right? So the planets around the sun move in ellipses. This is the sun.
What's a precession?
Right? What's a precession? Okay.
Is it something that moves
Wait,
in time? Or
hold on,
something?
hold on. Right. The planets move in elliptical orbit, right? So the place closest to the star is called perihelion. What is a precession? Yeah. What is precession? Who here did not take a course in advanced second year mechanics, classical mechanics? What? Mechanical analytic.
Didn't we talk about?
They must be joking.
No, we talked about physics.
In rotation motion.
Rotation motion.
Did you not speak about precession and rotation?
We did it.
Maybe in some years, but not always. In my year it was.
Hey guys, no, that's a secret here. Okay, precession is I sort of so I sort of draw it, right? So you have this this motion of elliptical motion, right? You can draw it like two circles, inner circle and outer circle, right? And the motion itself is an ellipse, right? But the ellipse is not repeating itself exactly, right? So it's nearly repeats itself, but when you go to the next trajectory, it will look something like that. And the next trajectory, it will look something like that. Right? That's how the motion really looks like. So if you look at the, this is the further away point. If you look at the further away point, this motion here, so it's sort of a secondary motion, right? The main motion is the ellipse, but you can look at the motion of the innermost or outermost point in the orbit, and it also moves, and that motion is called precession. משחקים בסביבונים בחנוכה? So there is the main motion. The main motion is around the ellipse, but there is a secondary motion, which is the change in the location of the innermost or outermost point in the orbit. That's called the precession. And you're supposed to learn about that in your classical mechanics. Huh? אני הראיתי לכם את זה, אבל זה לא חלק מהקורס במכניקה רגילה, זה לא חלק מהסילבוס. נתתי לכם אקסטרה, זה כן חלק מהקורס במכניקה אנליטית. וזה רע מאוד אם לא הראו לכם את זה. זה משהו שאתם אמורים להכיר. בכלל, תנועת סביבון. תמדו לכם תנועת סביבון במכניקה אנליטית. זה גם נוטציה, מה?
זוויות אוילר נגיד.
זוויות אוילר, בדיוק. צוחקים עליי. למה? למה לא היה?
נגמר הזמן, אבי לא רצה, לא יודע.
אבי עובד לאט.
אז זה לא רצה.
אבי לא מצא לנכון.
לא, זה לא רצה. זה חלק מהותי מזה. מה הוא עשה לכם? חשבון וריאציות הוא עשה?
2.5 הרצאות על קבועת.
לא, קפלר זה אני.
כן, בעיקר בתנועת קפלר הוא דיבר על פיזור.
פיזור זה בסדר, זה גם חלק מזה.
רוב הזמן הוא דיבר.
משפט נתר, המילטון יעקבי.
המילטון זה בסדר, אבל זה בסוף, זה לא צריך יותר מן המילטוניאן. צריכים את זה,
גם
לא?
המילטון יעקבי.
המילטון יעקבי בסדר, ג'קוביאן.
הרבה דוגמאות מיותרות.
זה שתי דוגמאות על המילטון יעקבי של קבועות.
קואורדינטות מוכללות.
טוב, כמובן שהדגמנו לגרנג'יאן שם כאילו, יותר מדי.
קואורדינטות יותר מדי. טוב, זה לא בסדר, אתם צריכים ללמוד את זה, צריכים להכיר את זה. זה רע מאוד שלא לימדו אתכם את זה. זה חבל, כי זה אחלה. זה זוויות אוילר ותנועת סביבון, בקיצור שמשחקים סביבון. צריכים להכיר. חלק מהסילבוס, זה משהו שצריכים להכיר אותם. תנודות קטנות הוא עושה לכם? אוסצילציה?
לא מספיק.
יהיה, מוסיפים שעות? טוב, בסדר. זה לא חלק מהסילבוס לקורס שלנו. אני אומר לכם פרצס, זה משהו שאתם אמורים להכיר אותו לפני שאתם מתיישבים. טוב, זה לא כזה מסוים, אתם מכירים את הספר של ג'קסון, לא ג'קסון, גולדשטיין. זה שיש לו את התמונה הזאת בדיוק על התמיכה. מה? כן? אתה מכיר אותו? אוהב אותו? תקרא שם, יש שם חלק.
קראתי טיפה, וכשהגעתי לחלק הזה...
הגשת? למה?
יותר מדי ביטויים מאוד מאוד ארוכים. וזה לא כיסינו את זה באנליטית.
זה מעגלי נראה לי.
מעגלי, כן, בלי פסיכי. טוב, אני לא יודע מה להגיד. זה חלק שאתם אמורים להכיר אותו, גם אם לא הולכים לקורס בפסיכות כללית, אני אוהב לדעת את זה חלק מפיזיקה. טוב, מה הדבר האחרון? הדבר האחרון אתם לא יודעים.
מה זה לא היה?
מה?
המבחן פה של...
תקף, נדבר על זה. לא, נציג את זה, אחד. מה הדבר האחרון? ואתם בטח לא יודעים.
כאילו אם אתה שולח איזשהו אות פנימה, אתה יכול למדוד את הדיליי.
שעשית שיעורי בית, כן. יפה. זה נקרא שפירו טיים דיליי. זה gravitational time delay. Time delay of a signal near gravitational potential.
גם כזה
מה? שנייה. זה נקרא שפירו טיים דיליי על שם אירווין שפירו. הוא אחלה בן אדם. הוא עדיין חי. הוא הולך בין 90. אחלה סיפורים מהפויה. היה איזה פעם שהייתי תקופה שהייתי פוסט-דוק במשרד לידו. זה גם בן בערך 90. חי ומשחק טניס. זה נקרא שפירו טיים דיליי. כמו של אירווין שפירו. כל הזמן שואל, לא פעם שנפגשנו, שואלתי שאלות שלא כאן. אחד החלקים הטובים בלהיות באוניברסיטה הזה, תמיד נתקע, כמה שאתה חושב שאתה חכם, תמיד נתקע באנשים יותר חכמים. זה מעולה. טוב. These are four independent measures, independent tests. Independent tests in the mean that each one of them is independent of the others. Each one of them give different results from between Newtonian physics and general relativity. Okay? And so you can test them. You know, when you have a theory, what you really want from a theory is some testable prediction that will tell you whether this is that can discriminate between this theory and other theories. And that's exactly what you have here. Right? So each one will give you different results between general relativity and Newtonian mechanics. They all have been tested, and needless to say, they all have been found in full agreement with general relativity. Okay.
The existence of black holes also proof. Can you explain it Newtonically?
What?
The existence of black holes.
Yeah, I mean you can. Okay, you're right that you can add to that. These are things that these are called classical. In recent years, you can add to that others which are not part of the syllabus, that is gravitational waves.
This was tested at Einstein.
No, this was no.
No, it could be measured, not measured.
No, not at all. The only this was the first one. Historically, Einstein knew about that. So this is the first that he predicted. So after he knew the measurements from Mercury, so he gave, it was a postage if you want. So Einstein knew that, and he saw that his theory can explain that. Deflection of light is something that's what made Einstein famous. That's a famous 1919 expedition to that shows that light when it goes close to the sun is being bent. It's studied by Eddington. I'll discuss that. I don't know if today, maybe on Thursday. Gravitational redshift of spectral length, I think we discussed that was an experiment that was conducted in the 1950s in Harvard. I don't remember the name of the answer. Shapiro time delay, Irving Shapiro suggested that in the 1960s, and the experiment was conducted in the 1970s. So Einstein was dead when this was after this. So this was 1950s, this was 1960s or 70s. Gravitational waves is something which is very new. You know that people have started to build that more think of building that in the 1960s, but it was actually measured only 5 years ago, 6, 7 years. 2015 was the first announcement, so it's already 9 years. If you want to add to that, that's called the EHT, Event Horizon Telescope. That's a black hole image. There are other indirect measurements, like saying that there is a black hole in the center of the galaxy. It's more tricky for the EHT because there are alternative models which were suggested to explain that. So it's not exactly direct proof that there is a black hole. EHT is the direct proof of light bending, but it's conceptually not that different than that. It works in a different regime, but conceptually it's the same thing. So conceptually, I would even remove that and say that gravitational waves, these are something which is conceptually different than anything that classical mechanics would tell you or anything else that there is. Okay. More questions about it? Gravitational redshift. That's something which we already discussed. Let's discuss. I won't have time to discuss all of them today, so we'll just start to discuss now. Oh, maybe quick now. Just give you a brief sketch, right? We already did talk about gravitational redshift, right? When we talk about the weak field limit, but now we don't need the weak field limit. Now we can do the full calculation, right? Let's talk about that very briefly. So we have source of gravity. Let's say this is the sun. We have two observers. And the observers are not along the geodesics, right? One is here and one is here. So we in R1, so we in R2. And we are not moving. So remember we had minus 1 minus 2 GM over R dt over d lambda squared plus 1 minus 2 GM over R minus 1 dr over d lambda squared plus R squared d phi over d lambda squared is a minus epsilon. So if they are not moving, that means that this is gone and this is gone. So the proper time right, just switch that here, so I got a d tau I over dt is a 1 minus 2 gm over r I power 1/2. Right, I just move that minus 0 excluded and move that, so that's all. Yeah. Epsilon is a 1. Basically, we can just get it directly from the Schwarzschild metric. Right. We keep the R0 and the omega 0. Now let's say that this observer 1, O1 and O2. So observer 1 emits a light that is being received by observer 2. Right? Now remember, d tau, what is d tau? Is the proper time. Proper time is the time for me. It's my time. You have your own d tau. Different. Now, T here is the time coordinate. So it's sending a light to the second observer. which sees the light is the same delta t. So we have delta t from here, right, is just 1 minus 2 gm over r1 minus 1/2 delta tau 1. Right. And for the second observer, delta tau 2, right, is just 1 minus 2 gm over r2 to the power 1/2 delta t. If I plug it in, this is just 1 minus 2 gm over r2 divided by 1 minus 2 gm over r1 to the power 1/2 delta tau 1. Now, rather than delta tau, what do we really see? We see frequencies. Right? We see photon frequencies, right? The sun, or some source of light, is emitting light to us. Right? So omega 2 over omega 1 is delta tau 1 over delta tau 2. Minus 2 gm over r1 over 1 minus 2 gm over r2 to the power 1/2. Of course, where r is much greater than 2 gm, which is a typical case, and we have omega 2 over omega 1 be 1 minus gm over r1 plus gm over r2. No, it's a half. Scalar expansion, right? So just 1 plus phi 1 is phi 2. Gravitational potential. So when phi increases, the frequency goes down. So when we're trying to climb out of a gravitational potential, the frequency goes down. So if I have blue light from here, when it comes out of the gravitational potential, it will become red. I'm exaggerating, but looks red, it's quite high, but the idea is clear. Yeah, question?
Which system is delta t measured?
Delta t is the coordinate. Delta t is the time coordinate.
Yes.
Right? So it's the same. Because I'm looking at coordinates. Like I have time r theta phi. If it looks strange, you think of r. R is constant here. Or it's the same coordinate, not constant. It's the same coordinate for everybody.
Okay.
So t, you can think of it as a coordinate. It's a coordinate which is the same for everybody. I know it's a little bit confusing. That's what I have to think.
Photon moves changing potential.
What? Photon, yes. So that delta tau is changing. Because I'm inside the. Essentially, it goes down here. It's the same thing.
Is delta tau is delta tau one time?
Delta tau is the
one?
proper time.
Yes.
So it is my time.
Yes, I know.
And you have your own delta time. Now, t is a coordinate time, which represents the entire space. So it's the same for all space. Okay? Same as r, right? You're located as a given r, given t, given theta, given phi, given x, y, z, whatever you want. Same as I. This is not changed. Your time is your time. My time is my time. I have to think of it. Okay, I think we're already running out of time. I want to remind you there is a tutorial at 12. Sunshine now. What?
What material is
Remember I promised you to talk about the geodesic deviation. So you might be talking about that, but you asked me. I also told you that I think I'll give you 2 problem sets this week because I'm spinning out. I don't have to, but I think it will be useful. Plus, there was at least one of you that said stimulating. Don't remember which one. Right.
I think it will record then. Okay. So, how is the course going, by the way? Because it's now, I think, more than 75% is already done.
Because it's so semester.
Hmm?
Because it's
Yes.
so semester.
I mean, but yeah, it's a short semester, of course, but the amount of the stuff that needs to be taught is already being taught. So I don't see anything which was reduced. Maybe you will not reach to gravitational waves and stuff, but that's.
He said it won't be semester.
Yes, he won't be. Yeah, that's what I'm saying. That he will not teach.
On that we should cover.
Good. Then that's more than enough, I think. Every year it's the usual thing. Oh, I'm going to use that, but later. I don't know why, but it feels like 1 hour is too less. So, we'll start with the geodesic deviation equation. I have made my own notes. I'm happy for myself that I made it. So, I'll put it on Moodle just because, I mean, the lecture notes that Asaf has, where he has derived the geodesic deviation equation, according to me, I would say, it's only the derivation of the equation which is written. And according to my feeling, I feel like that needs to be physical. When we are studying something, there needs to be some physical motivation of why we are doing that. So the geodesic deviation equation is derived in Asaf's notes. I have made some physical meaning of and significance, what is the use and stuff I have written in my notes. So I'll put it there and you can read it. Okay, so I'll read some of the stuff which I have written, like what is geodesic deviation equation? Did he mention anything, or he just like, okay, because he didn't have time, so he just left it? So he didn't talk anything about geodesic.
That minimize the interpolation. It's minimize the.
No, geodesic deviation equation.
Oh no,
He
we
said
just
you
said
will-
it's
No,
something
not
radical
geodesic.
and
I'm not
it
saying
didn't
geodesic
say
equation. Geodesic deviation equation.
He
Okay.
mentioned it, but didn't arrive.
He said you should.
Ah, okay. Deviation. This is equation? Yes. You people use that, or have anybody, you have seen anyone using? No.
I just did.
We saw you.
Oh, really?
No, it's
Yeah.
Okay. This is equation. Actually, it looks like alpha q power n. This is equation. Okay. So I'll read what I have written, like what geodesic deviation equation is. So the geodesic deviation equation describes how two nearby geodesics in curved space-time. I mean, it describes the what I can say. Geodesic deviation equation describes how two geodesics deviate from each other in the manifold. Like I take two geodesics, like two particles moving from each, moving like parallelly or whichever direction. After a certain time, how will they deviate from their original trajectory in a particular manifold? Like if you take the simple two-dimensional Euclidean space, what we have is like if there are two lines which are parallel to each other, will always remain parallel to each other. But does that same thing apply to sphere? No, because you have sphere. First half was good, and okay. So there was a plot, I think. Yeah, this plot in here, and whatever. let's plot only hemisphere.
Can you maybe switch a marker?
Actually, the way I'm plotting is not good. My marker is better, but I'm writing it in like slanting. Let's say a trajectory starting from here, trajectory starting from there. Initially they were parallel, but the end product at the end they crossed over. So what we are trying to derive in from here is like if there are two geodesics which starts from some initial condition, how will they deviate under the influence of upcurve, means in a curve structure because of the presence of a heavy mass or something like that. Okay. Yes, and then let's derive what it means. I have written so many things in paragraphs which I cannot read. Okay, so let's derive it. Derivation is simple, but there are few states which are not written, so you are supposed to know that step, or at least if you are not happy with that step, you need to go home and rederive it. Okay, consider a pair of free falling particle. Consider particles described by trajectory. I think this lecture note is already provided to you, where geodesic deviation equation is derived. It's in the curvature. Lecture notes of curvature, it is already there. So
Yeah, try and write it bigger, then I think you can see it.
ah, okay. You want me to write it bigger? Okay, I'll try that. Okay. I think, okay, it's not too big, right? Of tau plus delta x of tau. Good. Okay.
There should be just close the brackets.
Good. So it's the same thing that we are trying to derive is to look at the actually two freely falling particles. So okay, one thing that I forgot to mention is that here whatever is derived in this, means whatever I'll derive now is taken from Steven Weinberg's textbook. If you go and look at the lecture notes of Sean Carroll, he has defined it in the other ways where he directly make use of the Riemann curvature tensor and then derive it. Here we are not going to use the Riemann curvature tensor, instead we are going to use the parallel transport equation, and from there we can derive the whole thing. Okay, so now we have the two particles which has following the trajectory this and this. Let's write down the geodesic equation for them. Geodesic equation. This is for first particle that travels the trajectory, this one, and the second one would be everywhere I'm trying to write the capital X because my X looks like N, so I'm trying to avoid that. so that I'll still write x naught n. It's a little bit of lengthy writing equation, but there's nothing very okay. I just substituted the stuff and write the geodesic equation. Okay. Now if I start writing this big, I'll have terrible problem with space.
Maybe you can divide the board into.
You can curve the space.
Unfortunately, I cannot do it here. I don't have that huge weight with me, so mass is important here. Let's hope we can write some more stuff there. Okay, so what we are going to do is take the reference. Take the difference of two. This is equation 1, this is equation, oops, this is equation 2 to the first order in del x mu. First order in del x mu. I'm not going to write the subtraction thing because this is going to be very long, so I'm just going to write down the final product of subtraction. First, you just have to put this minus this, write the whole stuff, and then subtract, and I'll write down the final answer what I get after subtraction. Okay, so it will be d square del x mu by d tau square plus d gamma mu rho sigma d x alpha into delta x. If you see that I'm making any mistake in writing the indices, let me know, because there will be too many indices written on here. Sigma over d tau plus 2 gamma mu rho sigma dx over d tau sigma over d tau. Nothing fancy here, take the difference between these two. That's not visible from there.
I can't see
Oh, because of this.
yeah.
Okay, so we just took the difference between two. Now we are going to write the relative acceleration between the two trajectories. So I'll start from very top. Let's hope we can. First I'll write down, then I expect you to know what I'm writing, because this has already been taught like maybe 2 weeks ago. No, so we just consider that. So when you define trajectory, you define this lambda parameter. Instead, here I'm talking about the time. So Now this is my trajectory. Only thing that I need to worry about is how I define the lambda. My parameter which will take me 20. So it's like going on a track. I need to remember the very, what you call, very close proximity of where the thing is, and I can keep on defining that same lambda. I can define the whole trajectory of the particle. I'm making sense? Yes.
In the most bottom equation,
Yes.
the final term on the left side,
Yes.
what happened to delta x?
Yeah, in the final term, I think it should be gamma of x plus delta x. Is it because you took only the first order sign?
That's why. I mean, I have not written it explicitly. So you are saying that this term, why is this term not here? That's a brute force calculation you need to do. I mean, there's not. I mean, whatever this written here is not wrong. There is no approximation made. It's just the difference.
Okay.
So if you do the difference, you are supposed to get that thing. That's why I'm telling. There's no approximation or anything made here.
It's not like you took out second order terms.
No.
It's
That's what I already written that to the first order in del x mu. This is the most important thing in here. Just take the reference. You are going to get this thing. How did I write this thing in here? You remember this equation for parallel transport? It's the same thing. What I'm going to do is take the brute force derivative, like derivative of each term, and multiply stuff, and let's see where we reach. Okay, so it will be d square over d tau square del x plus derivative of yes.
You missed this inside the brackets of the tau, you've got delta x with no index.
Oh, yeah, sorry. That's segment. Sorry. Thank you. I expect you to know how to do those algebraic steps, because in exams you are really going to use, there is no other option. I mean, you will have to do whatever comes out in exam. So it's not like, what I meant to say is you need to know how to derive the stuff, the steps which are not written in between in somehow. Because this is just a simple algebra of multiplying and then contracting indices and, okay. Okay. Is this thing fine? So step that I have written in here. There are so many indices in here that you need to be really careful about. D square over d tau square. delta x mu plus 2 gamma mu rho sigma dx rho delta by delta of delta x sigma plus you see here there are some manipulations made. Bad terminology, not manipulation, some adjustments. Manipulation is wrong word. Manipulation means something that was not coming and you just put it somehow just to get the answer. So this is adjustment, not manipulation. My bad. Okay. It's a very big term. Gamma alpha rho sigma dx beta dx delta dx rho delta delta x sigma. In here I put the equation for parallel transport, and again here I put the same thing. For this I again put that same equation and I just multiply the whole stuff. Okay, so this is equation number 3. Let's write it equation number 4. Oh, yeah, we don't need to. What I'm going to do is, in this equation I'm going to somehow use this thing. So I already have, if you see in here, d square by this term. The first term is this one, and the second term there is the third term in here. Okay, so what I'm going to use is to this plus this equals to minus of this, right? That's what I'm going to put on there. Using equation 3. Even I don't remember how I started writing this way, but somehow I did. Because whenever we write TION, I never remember myself writing TION. TN. This is TION. That's how I understand. I don't know when I started writing that way, but mu rho sigma dx sigma dx delta delta dx rho delta into delta x sigma minus d gamma mu rho sigma dx alpha delta x alpha dx rho delta dx sigma delta. This is just this plus this equals to minus this, everything else the same way. Now the thing is, I'm going to do so many change of indices, all in the dummy indices. Yes.
In the third row, you have two terms. Before that, actually, you have two terms in the.
This one.
Yeah, you have two terms in the rightmost parentheses.
Yes.
I understand why the second one is there. Why is the first one?
So you mean this term, this whole term?
Yeah, the first one of those.
Yes.
Why is it there?
So okay, where is this thing? You just take the so first I took the derivative of this thing, and then I took the derivative of this thing. But this term I can again write this d by d tau of this again term del x mu, which again I can write it this way. So here okay, the first one is fine.
Yeah.
The second one, when I take derivative of this, and derivative of this, d by d tau of this term. How does it look like? D by d tau of this term. Here it is second derivative, I'm only there taking first derivative. So again, I write this term as like this one, the parallel transport equation.
And I'll look at it later.
The way this thing is written, this is exactly same thing written in here.
Okay.
Because here it was second derivative, so I took the first derivative and write the parallel transport. Here I only have the first derivative. These things are already multiplied to that. And I just multiplied, instead of writing this term, I multiply by this parallel transport equation.
I think I understand. I need to think of it a bit more. Yeah, I think I understand.
There's nothing crazy done in here. So I hope everybody else is fine with that. It looks really nice. Oh my god, how much time do I have? Okay, so what will I? Time, right. Oh, we have a lot of time. Good. Very good. Relabeling the dummy indices, what I'll do is to write sigma as alpha, sigma as alpha, delta as sigma in the first term. Third term, I'll do rho as lambda, sigma as alpha, and nu as rho. Fourth term, alpha as lambda, sigma is alpha, and beta is sigma. Change all these dummy indices in here and then write down the equation. This is good. People behind can see, yeah, I think they can. A mu would be d gamma mu rho alpha t tau minus d gamma mu rho alpha sigma. So this will be alpha, right? Yes, this is sigma over t tau. That's bad. lambda alpha mu sigma lambda rho alpha minus gamma mu alpha lambda gamma lambda rho sigma multiplied by dx rho over d tau dx sigma over d tau. No, this is again dx. Okay, doesn't matter. Delta x alpha.
Shai, in
Yes.
the third term, your name?
Yes.
In the third term, it's supposed to be sigma and sigma or sigma and alpha?
So which equation you are talking about? This one or the
No,
expression?
no,
Which one?
the last one.
The last one, okay. So
Yeah, in the third term, where you have the gamma and gamma, is it supposed to be both the sigmas
okay.
or
third term. So it should be alpha.
yeah, okay.
Where is the third term? Third term sigma 1, 2, 3. So sigma is by alpha. Third term sigma is alpha. Okay, so this is the. And what is this bracketed term? Does it look any familiar? Riemann tensor. Yes. This is Riemann tensor. I write nicely. Okay, so this is same as writing A mu is equals to Riemann tensor of R mu rho sigma alpha dx rho over d tau dx sigma over d tau into del x alpha. Yes. Okay. Now the thing is, this is derived, but what does it mean? Why do we need to do all these things? Anyone? Why is the need of doing all these things? Why are we doing this? I know this is derivation, this is part of syllabus, so we are doing it. It's fine, but
It tells you how the curvature affects the second derivative of the change in distance
yes.
between the genus.
And what does that mean? Okay, so it just says that because of curvature, because you see that Riemann curvature tensor. Yes, so it, yeah, exactly. They can be means. So the two particles are means the let's say two particles which are moving along some trajectory. Due to the presence of the curvature, it will deviate from its position. Okay, and the physical meaning of this is that yes, it or anyway we define the acceleration, so it represents the acceleration between the two geodesics which are moving along the path which have very small deviation from each other. Okay, so we are describing the two particles which are traveling along the trajectory tau and tau plus delta x mu of tau. So this thing represents how are the two particles traveling along the trajectory which are very close to each other will leads to the acceleration between the two particles. And okay, so yes, I didn't do anything. Okay, so what it says is that some of the parts are not derived. I mean, some things are not really included, not physically motivated in this lecture note of Asaf. If you read the second derivative of the, I already have written the second derivative. This also describes the tidal forces between the two particles moving. So because of the presence of curvature, there is a mass, means there is a mass, then there is a curvature, and if there are the two particles moving, they will get affected by the tidal forces. If you really want to read more about it, you can read from book of Hartel. And okay, what is the need of this thing? So it is helpful in understanding the curvature. So because if we have a curvature, it means that it warps the space-time, and those two paths which were initially parallel will no longer be parallel. And what are the other forces? Yeah, other things, that is the tidal forces. So in what I have written, in general relativity, tidal forces experienced by a body in gravitational fields are described by this geodesic deviation equations. And these forces are due to the differential gravitational pull on the different parts of body, which can be understood by the relative acceleration, which is described by this equation in here. We use it in astrophysical applications where we study for the black holes and neutron star because of the stretching of the space-times, that is the gravitational waves, where this is more helpful. Okay. So the main motivation of doing all this thing is because we can use it in all those scenarios. And why do we need to do this is because it tells us that, the same thing I'm repeating again and again, that two particles moving parallelly initially, because of the presence of curvature, they will feel the acceleration. Okay. Good. I have also given the Newtonian analog to that, which I am not going to talk in here. I will put this on Moodle, there you can read it. So is this fine? Okay, it's good. According to my feeling, how I understand things is like, for me, deriving this thing is not very something that you do very fancy. You need to understand what is going on. When I derive all these things, what I learn from this. This is not mathematics department. So the physical motivation behind is that why am I using this? What is the application of this thing? Why I get all this is more important. Okay. I don't feel like erasing. It looks so nice. Okay. Now we'll try to solve two small problems. Yes.
Please read that.
Okay, sure. Anyway, I'm not writing a single word extra than what is written in this lecture. So you don't need to copy paste. It's good if you are doing it for yourself. It's fine, but you don't really need to. Okay. So we'll use at least one, if time allows, two numerical problems. Okay, so the problem is, given the usual Schwarzschild metric as a function of r, what is the coordinate velocity of this? What is the coordinate velocity in this metric? In radial direction, in transverse direction, and what is the physical consequences of this result? Okay, I'll write down the equation. Do you want me to write down the question? I will write down. Given Schwarzschild, hopefully I'm right. Yes. Metric given Schwarzschild metric as a function of r, calculate or derive. What is the coordinate velocity? Coordinate velocity of light in radial direction is direction and transverse direction. And the part B is, this is, what is the physical consequence? Just physical consequence. Meaning. Very easy problem. Okay. We have a Schwarzschild metric given as a function of r, and we are asked to find the coordinate velocity of light. Coordinate velocity means the velocity in the coordinate which is written. Okay. In the radial direction, in the transverse direction, and what is the meaning of this? I think you have already studied the Schwarzschild solution, at least to some extent, if not fully. Okay. So, how should I proceed? Any idea? It's very easy. I mean, okay, not very easy. I mean, it's easy. Come on, you are doing more difficult problems and homework than this one. This is way too easy. So let's write down.
Function of what?
R. Sorry, this
okay.
radial. R.
Okay.
So we have a Schwarzschild metric. Let me know if I'm writing it wrong. Very simple. Yeah, exactly.
1 minus 2g m
Over R.
over gamma square. Over R.
Over R. Yes, that is what it is. Okay, so let's start for everybody. So we have, this is right. This is how you write the Schwarzschild metric. Okay. What is asked? Given the Schwarzschild metric as a function of r, what is the coordinate velocity of light? How do you calculate the velocity of light?
Divide by dt.
Sorry.
We divide by dt square.
Yes, so but light travels along the null geodesic mostly. So we just say that d square is ds square is 0. Simply. It's fine. You look puzzled. Okay. So what I am going to have written it. So to find the coordinate velocity in this metric, we need to consider the path where ds equals to 0 as light travels along null geodesic. So okay, from this solution you will should understand what kind of solution I want. When I say that, explain what you have written. Okay. So what I want is for the speed of light, for the light, that means it travels along null geodesic, ds equals 0. So this equals 0. Rewrite the whole thing. G over r, c square, dt square. Why am I writing the whole stuff? Oh, okay. I'm not willing to write that much. So let's start from A. What I want only in the radial direction. First thing is ds equals 0 for light. Okay. What I'm looking at only in the radial direction. What does it mean?
0.
0. What terms I have is only these two. So it's minus of 1 minus 2 Gm over R c square dt square plus 1 minus 2 Gm over R inverse dr square. Okay, this is equals to 0. Do some rearranging. So this is equals to minus of this. I'm just not willing to write stuff, that's why. Okay, this means this and this goes. Okay,
Yeah.
fine. So now let's write down the
principle of minimum function.
yes that I should not use, but I am somehow using it. There's nothing very. It's understandable, right?
Yeah.
Because here it was plus, which is equals to 0, which when I took it to the right hand side, this is minus, and this minus goes out. What I have is this one. And what I am going to do is,
Wait, how can you have such a trajectory assuming d5 is equal to 0?
This is radial.
No, it's radial, yes, but you're saying find velocity in transverse direction, right?
first I am finding out in radial direction, that's why I have written A. First I am trying to find out in radial direction. Second I will find out in transverse direction as well. So these are two separate questions. First I will find out in radial.
So there's just two separate trajectories.
These are two separate questions, yes, exactly.
The
Two separate,
The two separate trajectories.
of course. I mean, come on, how is this going to be possible anyway, if that's the case?
No, the trajectories which move both radially and transversely. There's complicated to solve. It's possible.
2gm over r dr square. Okay. So what I'm going to do is dr over dt is equals to here c square 1 minus 2gm over r square. Okay. That's the radial velocity. Okay. So easy. You are not going to be asked, I mean, exam this kind of questions is very rare it's going to be asked because it's too easy. Okay, so this is fine for the radial velocity. Let's calculate the, now I can erase it, right? Every day I bring at least 3 to 4 markers, thinking that I will write with all 3, 4 so that it will look good. But at the end I realize, okay, the DD is already done.
Excuse me, can I ask a question?
Yes, sure.
So, the speed near the event horizon.
Okay. We are going to go that's why I have asked the second question. Yeah, because that is more important thing from my perspective than deriving this, because this is too easy to do that. Yeah, we are going to go to that. That's why I did not erase. And okay, let's derive the transverse direction, not top. B it's. So what I am going to do is to derive. Okay, transverse direction means this is 0. Now I can take either theta or phi 1. So what I'm meaning is, like, I can take either this one or this equation to there, right? Either I can take theta to be d theta. Huh?
Symmetry.
Sorry.
Symmetry.
Yes. So what I have written in my solution is that I take d theta equals 0. You can take d phi equals 0. Doesn't matter. Okay. And let's take theta equals to pi over 2 for simplicity. So whatever remains is r square d phi square. Okay. So what is my equation is 0 equals minus of 1 minus 2 gm over r c square dt square plus. Okay. Yes.
And instead that you could take d phi 0.
No. Yes.
You
Oh,
could,
sorry.
You could have taken d phi 0.
I could have taken theta equals d theta.
But you cannot take d theta 0 and then let's choose theta pi 0. Pi
No, I mean, okay,
2.
so-
it is it's
Okay.
the same. It's You have to do it in one step.
Okay. Let's forget about theta 1.
Okay.
We will derive with the phi.
Okay.
P theta 0. Okay? We'll derive with the phi. Sorry. D phi 0. We'll derive with the theta. Okay? R square d theta square. It's not going to alter my result.
Yeah.
It's going to come out the same. Okay? This is the thing. Let's. Okay. Now, minimal work done. D theta over d t would be plus minus c over r 1 minus 2gm over r inverse. Oops, not inverse. 1/2. Okay?
The fish should be broken. What's written? You replace.
If you want, I can write the steps in between. There's nothing
Yes.
innovative in here, right? Okay, so now I have these two solutions. Now I want to ask you to give me the physical consequences of these two. Instead of me providing you what does it mean. What do you think what it means?
Well,
Look at the solution and tell me something about what you have.
if you move it on the radial direction, you get close to the velocity radius, then you slow down until you stop. Or kind of almost stop.
Okay, so that's the first part, of course. That's
And on the Schwarzschild radius, if you move like on that sphere, you
Mhm.
don't move the same.
yes. Okay, so that's what it is. Okay, so for everybody, let me. What does it mean if, let's say, okay, when r approaches to gm, what am I going to get? Okay, what I'm going to get as an answer, not the sorry? R is a yes, but yeah. By the time means when r approaches to gm, what will happen to dr by dt?
Very small.
It will approach 0. There's no, okay. So the coordinate velocity of light in radial direction decreases as r approaches to 2g. Okay? And what happens at 2g?
Say it again.
The coordinate velocity of light decreases in radial direction as r approaches to 2g.
And what about the velocity itself? No, not the coordinate velocity.
No, so okay. That's also, okay. I have written that. At the event horizon r equals 2gm, the coordinate velocity of light becomes 0. At r equals 2gm, this will be 0. Okay?
Well,
So-
I understand that in the coordinates,
Yes.
you get that you send the light to a black hole and it sort of stops on the
Yes.
event horizon.
Okay. Actually, it does not stop. That the meaning is that this indicates that it cannot escape. Once it goes in, it goes in. You never know the output or anything after that once it reaches 2gm for the Schwarzschild matrix. But we do not observe the Schwarzschild black hole.
If I'm at the core, at infinity, okay,
We are at that
and
there.
I want to know in infinity, if you put r infinity, you get c. Okay?
You get C. Yes, of course.
If I'm at infinity and I send the light directly to a black hole,
Yes.
what happens to the light velocity? From
That-
my point
okay.
of view, not from the coordinate there.
Yes. So for that, data soft raised to critical coordinates and stuff. You will get to know that in the later lecture. That's what I'm going to say. For here, what I'm saying that this is all because of the coordinate singularity that you see in the Schwarzschild metric at r equals to 2
Yes,
GM.
but I have my coordinates. I have my sort of rest frame root coordinates.
Yes.
What happens then? What happens in the velocity?
So at close to the black hole, you are saying.
Yeah. Or
So-
at any point.
So what you see is that I mean that's how we define like when we say about the black hole that okay, then when there is a light going on, once you reach the event horizon, that R and T reverses the sign, if you remember this.
Yeah, okay.
So what happens is that the light which goes in,
Even before, what is the velocity of the light as it approaches the event horizon?
you just see it from in here.
This is in coordinate time. I want to know from my coordinates, from my coordinates as an observer at infinity.
Okay. So, okay, what are you you are going to see is that some, what you can say, it's going to be like very much close to C, means but as you go on close and close to black hole event horizon, it's going to decrease, and at the after the point when it reaches, you don't see anything.
Let's say I'm at infinity.
You are at infinity.
I drop a stone. It's in free fall.
Okay.
Okay, and I want to think about the velocity of that stone.
Yes.
Is there
Is
there any difference from the Newtonian results? Because I know what happens according to Newton. Is there any difference for my perception of the falling stone? Is there any difference to the? I mean, you cannot tell me that the stone, as it reaches
the close to event horizon,
it has a zero velocity.
yes.
What does that mean?
No, okay. So, okay, whatever here we are talking about is from this coordinate point of view. Because in this coordinate system, you are saying as this exactly.
But the Schwarzschild coordinate system is it's sort of a not physical thing.
Exactly. But
So
when
I'm
you
asking, just as I sense a stone,
Yes.
a physical object, a massive,
I
and it falls. Is there any change from Einstein to Newton in that sense? Because I think there shouldn't be any change.
no, why would there be any change? Because the physical laws will remain same. If you go to very far distances are equals to infinity, where you are seeing, you see the Newtonian